Okay, so let's get started, please. Now, thanks, folks. I'm going to spend about roughly 20 minutes on introducing a new topic. And I'm just going to put on the board a whole lot of keywords, things that you need to be familiar with for this new topic. I've said it before, but I'll say it again. Everything that we do in chemistry is like, it's sort of sequential or it's foundational. So we started off with atomic structure, and then we went to periodic table. And then we went from periodic table, we started looking at bonding. And we spent a lot of time on bonding. And then from bonding, we started talking about acids and bases and chemical reactions. And the next extension of that now is mole concept, which is doing some real calculations, like in the real world with real equations. Okay?
Are we going to do more acid and bases, or that's it?
No, we'll come back to acids and bases. Everything we do is dependent on previous knowledge. So that's why we do things in a certain order. Okay? And typically we leave probably the hardest topic until last in semester one, and this is it. This is the topic that most people struggle with. So if you thought that you found bonding a little bit challenging, okay, this one, a lot of people really, it takes them a long time to click, okay? So the stuff we go through today, you might sort of, at the end of the lesson, think maybe nothing, all right? And think maybe I don't want to do chemistry anymore, all right? Because it's too hard, I'm going to cry, all right? I hope that that's not the case. So put it into context, just so you've got a bigger picture view. This is where we are actually sort of heading with the whole thing called mole concept. So what it actually does is this. So we talk about mole concept, and I'll give you some equations. You need to maintain these equations as well. Everything I'm going to do now, okay, is fairly critical. I'll record it anyway, obviously, so you can come back and grab it at some other point. So mole concept, it's short for the word molecule. That's where it comes from if you've done any reading. And it is all to do with chemical quantities. Quantities is what we're talking about. Chemical quantities. Now, we actually use a few terms in this new concept, right? And I'm going to introduce some of those terms right now. If I have an equation, for example, H2 gas plus O2 gas, one of the things we do with mole concept is we always start with an equation, because equations make the world go around, basically. Didn't know that. So I've got to balance the equation, which is what we always do. And so basically, the way that this works now is as follows. If I give you a quantity of hydrogen gas, typically as a mass, so the first thing you have to understand is that we record masses of chemicals, okay, and the unit we use is grams. So as soon as we start talking about an amount of chemical, we're talking about the mass of chemical. So we can basically do calculations based on this. So if I give you 10 grams of hydrogen in a cylinder, for example, and if I allow you to react that with oxygen, you can actually do a calculation. Once you know the mole concept, you can actually tell me how much water, liquid water, will be produced when I actually put a match to those two gases. You can do a calculation based on that. So if you think about in terms of what's happening with this in industry, if I'm, for example, making sulfuric acid, sulfuric acid is a combination of a couple of different chemicals, or if I'm making ammonia, for example, to go on and make a whole lot of other chemicals. If I actually say I want to create 1 tonne of ammonia, I'm not just going to go and get nitrogen and hydrogen, the two reactants, and put them in a big beaker and stir them together and think, oh, I hope that's going to work. Okay? It's not guessing anymore. Okay? It has to be very, very accurate. Similarly, as soon as you go down the pathway of anything that involves drugs or typically medication, because my wife is a pharmacist and she works with this stuff all the time, so one of the most important things that they have to work with is something called concentration. And of course, if I were a pharmacist and if I were prescribing, say, some type of a drug for you, for whatever ailment you have, I would need to make sure that whatever I gave you, whatever dose I gave you, I had measured out accurately, so that when I give you that dose, it's going to have its desired effects, and consequently, I'm not going to kill you if I overdose you with too much. So there's a calculation involved in the mass of your body, your blood volume. Then I've got to work out what is the thing that I'm trying to get into your system. Okay, I do a calculation, a mole calculation with concentration, and I say, okay, you need to have like 500 milligrams of, say, aspirin, all right? But that's the maximum dose you can have at any one time, based on your body mass. And so all the calculations that pharmacists do on a daily basis, all the stuff that industrial chemists do on a daily basis, and the stuff that you'll be doing in the lab in the next few weeks, involves understanding how chemicals react together by quantity. Not a random number, it's a quantity. In terms of the mole concept, we now have introduced, obviously where we can use it, we talked about a mass, but when I read this equation now, this is how we read the equation. 1, 1, and 2. So the way that we read this equation is like this. 1 mole of hydrogen, okay, reacts with 1 mole, and by the way, I haven't even told you that yet, but once we start to get into it, we drop the E off mole, alright? It's supposed to be shorter. It's only 1 character difference, don't ask me why, but that's what we do. 1 mole of oxygen, and the product from that is always going to be 2 moles of water. So the number out the front tells me a proportion of reactants to products. That's how we read the equation now. So the number at the front tells me how many moles are reacting. Omar? I'm just saying there's 2 moles, to be just clear on that, 2 moles of water molecules, yes. If I asked you how many moles of hydrogen atoms, you would say there's 4 moles of hydrogen atoms. Okay? We're heading down that track. We're not quite there yet. Alright, so, and I'm talking about 1 mole of oxygen molecules and 1 mole of hydrogen molecules. But I haven't actually even told you really what mole is yet. Okay? But I have used the word quantity, chemical quantity. So 1 mole is a count of particles. Okay? Should it?
Yes.
I think he's correct. Alright. Now, why did nobody else pick that up? Oh, I thought you were talking about this.
I was talking about the balance.
Gee, get it right. 2. Correct, 2 moles. So the ratio I got wrong. I got 1:1:2, but it should be 2:1:2. Now, that ratio is critical because that's the ratio that determines how everything reacts in that equation. Okay, so I'll say that again. The ratio determines how everything reacts in that equation. So 2 moles of hydrogen reacts with 1 mole of oxygen as a ratio of 2:1, not by mass, but by mole, to produce 2 moles of water molecules. Just spoke about chemical quantities. We haven't even talked about it yet either. So 1 mole is a count of particles. And the reason why we group them together, okay, as a count is they're too small, way too small. So 1 mole of anything equals 6.023 times 10 to the 23 particles. So we equate that with a number of particles. Well, the particles can be atoms, they can be molecules. If I said I've got 2 moles of people in Adelaide, that means I've got 2 by 6 by 10 to the 23. It's a lot of people, all right, in Adelaide. But of course, we're talking about individual atoms or molecules. We can't count them individually, so we'll just say, okay, let's group them together. We'll call that quantity the mole, okay? And that is also called Avogadro's number. So you'll see that word come up in all sorts of stuff. You'll see it in physics, and you'll also see it a lot in chemistry. So we call that Avogadro's number because he is the smart person that worked that out by doing a whole lot of experiments. So quantities we talk about is the mole. The mole is a count of particles, that's all it is. An equation tells us how things react in a chemical equation. The ratio that chemicals react in order to produce products.
So is the mole, when you say particle, you're referring to the atom itself?
Yes.
Each individual atom?
In this case here, it depends on how I read it. I could be talking about atoms, alright, but in this equation I'm talking about a molecule. A molecule and a molecule. Omar.
Would there be something else besides water that's what it's...
No, that's the only product for that reaction.
So where did the extra mole go?
Where did the...
Extra mole, there's 3 on one side, and there's only 2 on the other side.
2. There's 2 hydrogens. There is 4 hydrogens. There's 2 oxygens. And there's 2 oxygens. So the equation balances same number of atoms.
Yes.
They've just been rearranged.
Oh, yeah.
Okay?
Yeah.
Are you happy with that?
Yeah.
Alright. So we've introduced the idea of how do we measure chemical quantities? Well, we use the mole in the equation. Okay? But we have to use mass to allow us to work out the number of moles. So I've got to now introduce another term. If you have your periodic table handy in front of you, and I'll just look at mine over here. All of the atoms, you will notice, have got associated with them the atomic number and the mass number. Yes? Does anybody know where that came from? Where the mass number come from? So why has hydrogen got a mass number of 1.007? And why is, say, manganese 54.938? Where do those numbers come from? They're not a whole number because of isotopes, that's correct, Senna. They're not a whole number because of isotopes, alright? But where do those numbers originate from? Samuel? It's the addition of protons and neutrons, okay? But, alright, if I were to compare, okay, a hydrogen with a carbon, let's do it with oxygen, okay? If I had 1 mole of hydrogen, I actually have got 1.00797 grams. If I have got 1 mole of carbon, it is 12.011 grams. If I have got 1 mole of oxygen atoms, I've actually got, where are we, 15.99 grams. Now, that's called the molar mass of the chemicals. Molar mass is the weight of 1 mole. So where we're heading here is that when we look at all of the elements in the periodic table, although I use the word, and I've used it before, like the atomic weight, okay, I should probably be using, depending on what I'm talking about, I should be talking about the molar mass, okay, or the relative atomic mass. Relative atomic mass or relative molecular mass, or relative formula mass. They all mean the same thing at the end of the day. Alright? Now, everything on the periodic table is compared to carbon-12. Carbon-12 is the most abundant element, and so we've used that as a standard to measure the weight of 1 mole of every other element. So what we're saying then really is that if I had 1 mole of carbon atoms, it's going to be 12 grams. If I've got 1 mole of hydrogen atom, it's going to be 1, which really is saying that a hydrogen is like 1/12 the mass of a carbon atom, if I'm comparing them side by side. If I was going to compare a carbon with a hydrogen, well, with an oxygen, so an oxygen, okay, is about 4 grams heavier than a carbon atom, which is what we'd expect. It's got more protons, it's got more neutrons. So we use carbon as a measure of the weight of everything else in the periodic table. So we call that relative molecular weight, or relative formula weight, or relative atomic weight. Give you an example. Let's have a look. So if I asked you, for example, what is the relative molecular, and I use these words interchangeably, probably a bad thing to do, okay? What do we use in the book? They use mass, so we better be consistent. Relative molecular mass. So if I asked you what the relative molecular mass of water is, you have to add up all of the hydrogens and all the oxygens in the formula. And so it would be this. It's going to be 1.00, I'll put it to 8 times by 2, and then I've got to add to that 15.999, and the answer is, what is it? 18 point what? 18, alright, so when we add it up, okay, we'll get an answer around about 18, okay? But we haven't talked about sig fig yet, that's another story. So what would actually say, for example, that the relative molecular mass of water is 18. Now I need to use that in the calculation of moles that we'll talk about shortly. If I gave you just a hydrogen sitting by itself, this is called the relative atomic mass, and the reason for that is that it's only got 1 atom. We're talking about 1 atom. That's where the word atomic mass comes from. But how do I get it? I go to the periodic table, I look up Earth for hydrogen, and it comes out to be 1.008. Ricky?
Isn't hydrogen the most abundant element in the universe?
No, we work on carbon. Yeah, carbon.
Why is that?
Because most of the chemicals we come across are carbon-based, they're all organic. And the basis of organic chemistry is carbon, hydrogen, oxygen. But we use carbon, okay, because it's the most accessible as well. Carbon's a solid, hydrogen's gas, alright? So it's a bit easier to work with carbon as well. Alright, if I gave something like this, okay, we now go into an ionic compound. Been watching? Alright. So I would now call this a relative formula mass. So it's not a molecule anymore. Okay, we've turned it into an ionic compound, we just call that a formula. So we take it to sodium and chlorine, we add them together. And so the sodium is 22.98. 2.98. Chlorine is 35.5. We add them together and we get, what do we get, Shan? What do we get? 58.48 is the relative formula mass for sodium chloride. Now, units, well, we don't actually talk about units normally once we get into it, but the units for all these are atomic mass units, AMU. AMU.
Didn't you say it was grams on the top?
No. This is called the molar mass. This is the relative atomic mass. These have got units, okay, atomic mass units. The units for this is grams. Okay, questions? Anyone stuck on that? Yes?
Is there a particular figures you work with, or is it like depending on what the question asks?
We're not going to use it yet, but we'll introduce it in the short term. Okay? So we'll do that in the short term. But we won't get to that today. You need to use sig fig for year 12 as a given. Alright? But because we haven't really talked about accuracy in an experiment yet, we won't really probably do that until we get to the experiment stage. We'll start with titrations. We do these calculations. Alright? Now, so we've got the terms mole concept, comes to molecule. We know what 1 mole now is. And an example of that, I'll run a video next lesson, but the idea of a mole is no different than a dozen. Right? We use the word dozen, which means a count of how many? 12. We group it together in a dozen. It's easy. Right? So we actually group atoms together into an amount called a mole. That's it. We're just counting. Just a lot more fingers than 12. Okay? 10. Alright. So, the other thing we spoke about was the relative mass, or the relative molecular mass, atomic mass, formula mass. I don't use those terms. You'll find me use those terms interchangeably now, because the calculation at the end of the day is the same, as you'll see. Okay? And now we're going to have a look at how we work with that equation. How is that going to help us, and how we actually do some real calculations.
So formula mass is just for ionic compounds?
Just for ionic compounds. Atomic mass is just for atoms, and molecular mass is for molecules. But all we're worried about is how you do it. How do you do it? You go to the periodic table, look up all the numbers, okay, which is the relative atomic weight of all the chemicals based on carbon-12, add them together, and that's your answer. We're not worried about significance fig yet. Tony?
With the since 1 mole is equal to 6.02 grams.
Yeah.
I think then it's like 1 mole is equal to the mass of 1 atom.
1 mole.
Like, because you know they're like the 1 mole is equal to the 6 one.
Yeah.
1 mole is equal to the difference for each.
Okay, let's just run through that now. Okay? Because this will help you to work that out. Well, I hope it will anyway. The next thing is an equation that you're going to get, hopefully you'll get sick of using in the next few weeks. And it's going to come up for every question that we do. And I'll give you a sequence of things to work with shortly. And it's the same for every question you are ever going to do with mole concept. Okay? And the equation looks like this. N is equal to the mass over big M. N stands for the number of moles that the chemical is we're talking about. The mass is always in grams. Now M, big M, we call it, like big M the milk type thing. So big M corresponds to either relative molecular mass, if it's a molecule, or relative atomic mass, if it's an atom we're working out the moles for, or relative formula mass, doesn't matter. Okay? So I'm just going to put down here, okay, the atomic mass, but it refers to any one of these three. Okay? Now, if I wanted to work out, for example, let's work on this one here. If I wanted to work out for this, the number of moles of hydrogen gas, if I wanted to work that out in this equation, well, the equation I've got to use to work out the number of moles is N equals mass on big M. The mass I'm given is 10 grams, 10, over, now it's H2. H2 is, oh, we didn't have it over here, did we? But it's 1.008 times by 2. So can somebody work that out on their calculator for us, please?
So you said the mass is always given.
Yes, the mass will be given.
4.96.
Okay, 4.96 moles. Okay, here's the crunch. So we've worked out from this that we've got 4.96 moles of hydrogen. I'll put it underneath that in red. 4.96 is what we actually have got. Okay? Now notice that I didn't do anything with the number in front when I worked it out in an equation. A lot of people want to double the molecular weight for hydrogen, but the number out the front simply tells me the proportion the chemicals react in. 2 is to 1 to 2. With this equation, it will be the same today, it'll be the same tomorrow, and it'll be the same next week, and it was the same 100 years ago. Hasn't changed. That's the proportion that they react in. Now, I actually don't have 2 moles of H2. I just worked out that I've actually got 4.96 moles if I'm working with a mass of 10 grams. Who can tell me, this is a bit of a jump, who can tell me how many moles of oxygen then would react with 4.96 moles of hydrogen according to that equation? Think about it, talk to your partner. I'll count down. I'll count down from 10 seconds to work it out.
But the mass is not given for oxygen.
No, I want to know the number of moles of oxygen that's going to react with it. I didn't ask you for the mass.
And you want
It's 2 to 1, so we have
The mass and the mass of hydrogen.
Okay, put up your hand if you think you got an answer. Who can tell me how many moles of oxygen are going to react with hydrogen according to that equation?
2.45. You do
2.45. How'd you get that, Shem?
half of.
Half.
Because it's 2 to 1 ratio.
Okay. It is 4.96 over 2. That's the moles of oxygen that's going to react based on this ratio. Now, if you've done ratios before, maths comes in really handy. Okay? If you didn't get ratios, go back and learn it in year 8 when we did it. Alright? So, 2 is to 1. So if things are reacting in this proportion, okay, I need to have half. 1 divided by 2, half. It's going to be half the quantity of whatever that is of oxygen that I'm going to need to react with the hydrogen according to that equation. What I'm going to introduce to you now is something called stoichiometry. We just did it. Okay? So once we start doing calculations based on equations, we call that stoichiometry. Fancy name, okay? It's just a way of applying mole concept to a reaction. That's all it is. All right, can anybody tell me then, how many moles of water are we going to get as a product? Hands up if you think you can tell me how many moles of water we would get.
6.1.
The ratio is 2 is to 2, which is the same as 1 is to 1 when I went to school. Still at school? Hasn't changed? 4.96 moles.
What happened to the O2 here? Yeah, what happened to that? Don't you add stuff?
Sorry?
Don't you add the oxygen as well? Yeah. 4.96 to last.
Add the oxygen.
Yeah.
Explain with me, Parent.
You know how the moles for hydrogen 2 is 4.96?
Yep.
And for oxygen it was 2.4. 2.43, whatever.
Yeah.
When you add them together?
No, it's not like an equation where we don't add this and this to give this. It's not like an equation, like a mathematical equation. All right. We use the ratio of the equation to work that out. All right. So although it says plus, no, we don't take 4.96 and add 4.96 over 2 to get our answer. No. So let's get that clear. All right. It's not like 4 plus 2 equals 6. It doesn't work in a stoichiometry sense. Okay.
So because if the ratio is 2 to 2, it's the same.
2 is to 2, or 1 is to 1 is the ratio. Now, have a go at this. If I had to work out from this equation the mass of water that is produced from the reaction, any ideas how we would do that? So the question is, going back right from the beginning, if I have 10 grams of hydrogen, and if I react that with excess oxygen, what does excess mean, by the way? Ricky? More than I need, so I'm going to have some probably left over, but I need at least how much? How much oxygen do I need? Brandon? How much oxygen do I need minimum? 2.48, whatever that is. 4.96 over 2. I've got to have that at least. Okay? So I need that at least. That's why I said excess initially. Okay? And I'm going to end up with 4.96 moles of water. The question is, what mass of water? So how much water would I get if I did that reaction in the lab? What's its yield going to be? Let me say it again. What mass of water would I get from that reaction if I let the reaction go to completion?
When you times 4.96 times by 2?
Formula? That's a good idea. Let's use the formula, because what do we know now? Well, N equals mass on big M. We want to work out the mass of the product. So the mass is N times by big N. Do we know the number of moles of water produced?
Yep.
We do. 4.96, that's the moles of water. Do we know the molecular weight for water? 18, we'll use 18. Answer? 89.28 grams. So I get 89.28 grams if I react 10 grams of hydrogen with enough oxygen. It's going to yield for me, provided everything reacts, 89 grams of water. You can do a calculation, okay, based on that. Or I could have reversed the whole question. I could have told you, if I want 100 grams of water, how much oxygen and hydrogen do I need to add together? There's another level. I don't want to go down that road yet. Okay? Alright, so what do you need to know? This is what you need to know. 1 mole is that many particles, 6.023 by 10 to the 23. You need to know this equation. N equals mass on molecular weight or formula weight, okay, or atomic weight. They're all the same number, okay. You need to know, basically, also that everything is based on carbon 12. We call it an atomic mass unit. That's the third thing you need to be able to calculate, okay. And what else is to that's about it, okay, for today. That'll get you through. Sit down.
I don't understand how water is 4.96 moles.
Let's not go down that track yet, okay? Because what I've done is I've gone through a week of stoichiometry in one lesson. Actually, in 20 minutes, 25 minutes.
Where did you get the 4.96 from though? Like, you you don't add them together. You don't add the two
Okay, can I get rid of that now and I'll elaborate. Are you ready? Okay. Just so that people, you know, don't get confused. Okay, now let's run back and I'll do it in a different colour. That's not good if you're colourblind. Watch. 10 grams. So, now watch, and I'll run through this for everybody's benefit because you asked the question. Okay? So we used this, and then we used our equation N equals mass on big M to work out how many moles of hydrogen we had. Didn't we? And we come up with an answer of 4.96. That's what we calculated in our equation. We haven't got 2 moles, we've got 4.96. Okay? Now, the whole concept is based on an understanding of what the equation is telling me. The equation tells me that it goes 2 is to 1 is to 2. Everything in that equation operates off that ratio. It's called a stoichiometric ratio. That's where that word comes from. It's a balanced equation. By the way, if your equation is not balanced, all your answers will be wrong. Yeah? Okay? So we'll talk about that in a minute. Alright, so 2 is to 1 is to 2. Your question was, how did I know that I'm going to get 4.96 moles of water? The ratio is, here it is, the ratio of H2 to H2O, and I'm looking at those two things, is 2 is to 2, which is the same as 1 is to 1. So therefore, if I've got 4.96, that means I must end up with 4.96 over here if the ratio of the chemicals are 1 is to 1 in the equation. How did I get it? I got it from the balanced equation.
Okay, but what if you had 3 to 2 to 3?
I'll get to that in a minute.
What about the O? You leave it out?
No. If I were to go to the oxygen, we worked out that it was 4.96 over 2. That's the number of moles of oxygen. How did I do it? Okay, this is what's happening in the background. So I looked at hydrogen and I looked at oxygen. And then I looked at the numbers in front of them. 2 is to 1. That's the ratio that they're going to react in that equation. Therefore, if I've got 4.96 here, to go from here to here, if it's a ratio of 2 is to 1, multiplied by 1 over 2, 4.96 over 2. That's the moles of oxygen that's going to react to that. We'll come back to this again and again and again. Don't worry about it, we've got about 1,000 questions. 500 questions we're going to do. Okay? Alright. Now, any questions? Because what I did do in terms of the equation was advanced. Okay? Didn't plan on going that far. Alright? So there were four concepts there. 1 mole, the atomic mass unit. What else did we do? 1 mole, the atomic mass unit. The stoichiometry and the balancing the equation. And what else did we do? That was about it, wasn't it? Okay? There's a lot to try and absorb. Okay? One last thing, because I talked too much, but let's finish it off. From now on, I did say there are some very important steps that you'll write down, and you'll follow these religiously from now on. Okay? Whenever you are doing anything that involves mole concept, okay, you will consult the Mole Bible. Okay? Here it is. Whoops. And you won't go wrong. Number 1. Sorry? Not molar, yeah, I just thought of it. We'll call it the moly Bible, okay. Alright. First thing is, copy it down. First thing is, every time, listen up, copy this down now, somewhere prominent in your notes. The first thing you'll be doing with any question that we do from now on is balance the equation. That'll be your first check. Okay? The second thing is, you'll have to work out the moles. Now I'm going to use the word known. The moles of the known chemical. In this one here, what was the known chemical? Where did we start? H2 was the known. Have you done this before? Have you done this before?
No.
He's pretty good at it. Alright? This is the known. So anything that you've got a mass from, initially, you've got to work with that first. That's called the known chemical. Number 3, you work out the mole ratio of known to unknown. We did it. We had 2 unknowns over here. We had oxygen and we also had water. So these are the 2 that were our unknown. We're trying to work out how much of this reacted and then how much product we got. They were our unknowns in this scenario. Ben, watching. The last thing is, then once we work out the mole ratio, then we can work out the moles of the unknown. Okay, and then we could put a 5th step in, work out the mass of the unknown, which is what we did. You told me how much water is going to be produced. Okay, I could then go further, and we will eventually. I could ask you to work out the concentration of the unknown, all sorts of things. Ricky.
What is the before saying again, sorry?
Mole unknown. Okay, here is another key from now on as well. So here we've got the Moly Bible. Alright, but you will notice that you can't do anything without working out the number of moles. So if I asked you a question from now on, 99% of the time the answer will be calculate the number of moles, Mr. Campbell. Okay? That's what the answer will be. So if you don't know the answer, and you say that, you might look smart to the while. Okay? Because we can't do anything in any stoichiometry question unless we first transfer everything into moles. It's got to be in moles. Okay? Cameron, what's the answer? Moles. He got it right. Okay? Well done. Alright? Sham, what's the answer every time? Moles. Good. Go to your Moly Bible, look up moles. Okay, have a drink. Let's go, please.